like or not, we can share it into the folder later.
Okay.
Yeah, go
Uh,
ahead.
so, all right. So first thing, I don't know if I did the best job of like explaining this in the notes. I mean, I did, but I did it all with the handwriting, and I probably should have definitely included this slide. So, these are just like general formulas for finding the recursive rule and the explicit rule. So if this isn't stuff that you've written down yet, it is stuff that y'all should write down. It's also, are y'all on your computers? Um, what's it, Jarell and Anselmo? Hello? Can
Yeah,
anybody hear me?
yeah, I can hear you.
Okay, because y'all could also, right now, if you're seeing this, you could take a screenshot of it so that you have this going forward, right? Because this is all
Miss
stuff that
Kirk,
I
do
have
you know the buttons for screenshot on the? Are you guys on Chromebooks?
Phone,
to.
I can do it on the phone.
Okay.
I used to know how to do it on a Chromebook.
All right, Miss Kirk, we only have
Yeah, I
15
actually
minutes,
don't
so
know
we
to take a
can.
screenshot on the phone, but I ain't gonna recap.
It's Control plus Show Windows, that like little like rectangle-y thing at the top.
Don't worry, guys. I will take a picture of this and I'll send it to
But
you.
I'll also put this up so you'll be able to get it again. Okay, so and then there's this thing, the zeroth term, and I'll explain what that is as we go. So we'll skip these since we've already done those, and we'll start here. So the first thing it says, determine whether these are arithmetic or geometric sequences, and then write a recursive and explicit rule. The first thing I got to do is look at the pattern. So I'm seeing +4, then I'm seeing +12, and that right away, because it's not a common difference, tells me that this has to be some sort of geometric sequence. It can't possibly just be a recursive thing. I mean, sorry, it can't possibly just be an arithmetic one. So then I got to decide what the rule is, and then that brings me back to this whole deal where for recursive, geometric, it's this thing
To kind of
where
stop Miss Kirk there for a minute. Are you guys understanding the difference between a arithmetic sequence and a geometric sequence, or do you guys kind of
Kind of,
need us
sort
to
of.
kind of explain it a little bit more in detail?
Explain.
Kind of, sort of. Yeah,
Okay,
explain.
so if you guys see, you see the numbers on number 12. It says 2, 6, 18, 54. Do you have to? You're looking at the pattern of it, right?
Mm-hmm.
And the main thing for arithmetic sequencing is the pattern is addition and subtraction.
Okay.
So if I tell you the number 2, 4, 6, 8, 10, 12, is that's adding 2 to each time, right? So that's an arithmetic sequence.
Okay.
Okay. But if I
Uh-huh.
did, um, what's a geometric sequence? Times 2. So I can do like 2 times 2. So it would be like 2, 4, 8, 16. That's
Mm-hmm.
multiplying times 2. So that would be like a geometric sequence. So if the rule of the pattern is addition or subtraction, that'd be an arithmetic sequence. And if the pattern is either dividing or multiplying, it is a geometric sequence.
Mm-hmm.
Um, one thing in the past before that I kind of ingrained in the kids' head, if you look at arithmetic, it starts with an A. So just kind of allude to the word add. So it's add and subtract. So if that helps.
okay. So this recursive thing, I think the terminology and like the notation is what gets confused. AN is like any term, any random term in the sequence. So like this is term 1, 2, 3, 4, 5, and then the sequence could go on and on forever. AN minus 1 is just whatever term comes before AN. So if AN is 2, AN minus 1, 2 minus 1 is A1. If AN is A5, then AN minus 1 is A4. Do y'all get that?
No.
Yes.
So it's just like if I'm saying that 54 is AN, then 18 is AN minus 1. Does that make sense?
Yes.
So now to find this rule, I'm just going to plug everything in. I'm going to say I'm using A2 and A1. I'm going to plug the the big one on the outside and the small one on the inside. And then I'm going to solve for R because that's going to give me my common ratio. It's 3. And now I have everything that I need. So for recursive, we're like AN equals, well, really, I should probably write the 3 here. 3 times AN minus 1. Now for, what's it called? Let me change the colors. For explicit, my formula is going to be for a geometric sequence, AN is equal to, wait, it's actually really,
2.
for this, I really should call it A1. I should go back and fix that. A1 times R to the N. So that means, so in this one, N is the exponent. So for explicit, that's going to mean AN is equal to, or A1 is 2. And then R is 3 to the N. Can I go to the next one?
Oh, hold on. Now you can't.
Okay.
I like how you skipped straight to number 12 and didn't do 11. That's cool, though.
Oh, that was just an accident.
Like, can you go back so they can write it down, though?
To what?
There you go.
That's why I screenshotted it.
Hey, let us know if you're good, Anselmo.
I got it.
Cool.
Okay. I'm going to go backwards to 11 now. Sorry. Okay, so I'm going to look at this. I'm going to look at what the pattern is. So I'm seeing plus 7, plus 7, plus 7. That the fact that plus 7 is constant, that means our common difference is positive 7, and that makes this arithmetic. Okay, and so this is where this whole concept of, so you've got for recursive, oops, that's supposed to be, so for recursive, we're looking at AN equals AN minus 1 plus whatever the common difference is. So any random term is equal to the term that came before it plus the common difference. That's like any random term is AN is equal to the term that came before it plus the common difference. And then for explicit, we're going to say any random term that we want to know like the value of is going to be equal to the 0 term, that is the 0th term, plus D times the term number that we're looking for. So like When I say this is the first term, that means n equals 1. Second term, n equals 2. Third term, n equals 3, 4, 5, and so on and so forth. So now it's like, well, what is this? Well, I have to imagine some term that came before 1.
This is why I really like using a table.
So A0 is going to always be A sub 1 minus D every single time. So D is 7. So A0 is going to be equal to A1, which is 1, minus 7. So A0 is going to be equal to -6 here. And now that literally tells us everything we need for these formulas. Because for recursive, we're just looking at, we just have to plug everything in. AN is equal to AN minus 1 plus 7. And for explicit, we're just going to plug in A0, which is -6. So AN is equal to -6 plus 7n.
Okay.
If that doesn't make all the way sense, after you see a couple, it'll be more clear. Let me know when you guys are ready to go to number 13.
I'm ready.
We're ready to go to 13.
Okay, so the first thing, I have to look at the first difference and see if it's constant. So 10 to 6.5, I'm adding 3.5. I'm adding 3.5 again. I'm adding 3.5 again. So we're seeing that it's arithmetic with a common difference of positive 3.5. So our A1 is -10. Our A0 is going to be -10 minus 3.5 to give us -13.5. And that's literally everything we need to know. Because for recursive, we're going to be saying AN is equal to AN minus 1 plus D. For explicit, we're going to be saying A sub n is equal to A sub 0 plus D times n. And that just gives us, if I plug everything in, A sub n is equal to A sub n minus 1 plus 3.5. And then for this one, A sub n is equal to -13.5 plus 3.5 n. Does anyone have any questions about that one? It's totally okay if you have questions or you need to see me do something over again.
You good? I see.
Does it make sense, this A0 thing?
Yeah, it makes sense.
Is like the most important thing